Hi, my name is Mutlu Dogrel. I'm a cloud solution architect focusing on data and AI as well as MLOps working within Microsoft UK. It's a great honor for me to be speaking to this audience today in the DevOps forum. So today in this talk, over the next 20 minutes or so, I will be going through the concepts of machine learning, MLOps, machine learning operations, what the phases of ML lifecycle look like, and eventually talk about the tools that Microsoft uses to enable an end-to-end machine learning lifecycle. Machine learning, or ML, is the study of computer algorithms that improve automatically through experience. The term machine learning, or ML, is not new. In fact, it was coined in 1959 by Arthur Samuel, and it was defined as the ability of the computers to learn through an iterative process without being explicitly programmed. AI is a widely used term. It's a science of making the computer behave in such ways which are commonly thought to require human intelligence. Basically, AI, or artificial intelligence, is all about making a computer act human in some ways. Machine learning is simply a branch of AI. It's a study of computer algorithms that automatically become better through experience. ML is one of the ways to achieve AI. Machine learning requires large data sets to work with in order to examine and compare the information to find common patterns. We keep hearing about deep learning and neural networks as well. They are simply subclasses of ML. Machine learning and statistics are closely related fields in terms of methods, but they are distinct in their principal goal. Statistics draws population inferences from a sample, while machine learning finds generalizable predictive patterns. There are three main approaches that we commonly see in machine learning, but the list is not limited to three. These are supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, the computer is presented with labels, with example inputs, and their desired outputs given by a teacher, us, and the goal is to learn a rule that maps inputs to outputs. If you have some t-shirts that we want to classify, what we can do is we can present some labeled t-shirts, labeled as small, medium, large, and we use a classification algorithm that will make use of some of the features presented, and it will learn how to associate the inputs to outputs. And when we present it with a new unseen t-shirt, it will hopefully be correctly classifying it as a medium or a large t-shirt. In the case of unsupervised learning, there are no labels given to the learning algorithm, leaving it on its own to find structure in its input. A very typical example is clustering. And if we continue with the t-shirt example, if let's say we want to obtain 5 different classes of t-shirts of small, medium, large, etc., in that case, we just give the number of buckets that we want to end up with, 5, and we present the entire data that is not labeled, and the machine learning algorithm in this case tries to put together all the t-shirts that are similar to each other in the same bucket. In reinforcement learning, a computer program interacts with a dynamic environment in which it must perform a certain goal, such as driving a vehicle or playing a game against an opponent. Chess and Go are two good examples where computers excelled in this. And these are typical reinforcement learning based approaches. So in reinforcement learning, as the algorithm is navigating its problem space, the program is provided with feedback that is analogous to rewards, which it tries to maximize. It's really the carrot and stick approach. In a, let's say, simulation, car simulation, if your car hits the curb, then you penalize it, and hopefully it will learn from this mistake, and it will generalize the learning in future encounters. There are other approaches of machine learning, as I said, and there are many different algorithms under each category of machine learning. Deep learning, we mentioned neural networks, but it's not limited to these popular approaches. There are support vector machines, etc. As you can see in the top right corner of this slide, there are blue and red dots that we want to separate, and because there isn't an easy solution that allows us to separate the dots, we map this into a higher dimensional space where it's easier to find a hyperplane that can do the job. And that's another example of how we can do classification using mathematical tricks, kernel approaches. So the bottom line is machine learning is now everywhere. It's present when doing weather forecasting, doing face and speech recognition, traffic prediction, product recommendations, and of course also developed ML models can be embedded pretty much anywhere within IoT devices, sensors, on cloud platforms, in our cars, or even on our local computers to improve our lives in a multitude of ways whenever needed. As AI is so omnipresent, it is essential for the process that generates and enables AI to be more robust and systematic as well, as this will give way to reproducibility, auditability, model traceability, model efficiency, and performance, as well as better collaboration amongst data science teams. So let's first revisit the ML lifecycle. As a data scientist, you start by getting the data that have been curated to some format, and then you start experimenting with your data, doing any further data cleaning, featureization, etc. And after training your model or trying different ones, eventually you conclude with the one that fits your business model. Then you package it along with all its dependencies so you can actually run it and get value out of it. And then you go ahead and validate it, making sure that it is meeting your expectations in terms of accuracy, performance, any sort of regulatory compliance. And then is the deployment part, where you actually start getting value out of it and use the model to make predictions. A lot of data scientists think deploying the model would be the last step, unfortunately. But there is one more step. The last part here is monitoring. You want to make sure that you are constantly monitoring the model to make sure it performs the way it is designed for and gives you the values that are expected. If you build a weather forecast system for the UK, and if someone plugs your ML model to do weather prediction for a Caribbean island, this would be a major data drift. Once you see that ML model performance is getting worse, you need to come back to the initial part of the pipeline, kicking it off all over again to retrain the model. That is the ML lifecycle in a nutshell. And now let's talk about MLOps. What's MLOps? MLOps brings the DevOps principles to your machine learning workflow. So let's talk about MLOps and its key elements now. MLOps brings the DevOps principles to your machine learning workflow. So it's all about integrating CI/CD into the data science workflow. MLOps resembles DevOps for software development, but instead of the software development cycle being at the core process, now we have our ML lifecycle. So it's automating the building and testing of your code, creating these repeatable training pipelines, and then deploying your ML model into your target infrastructure. Also, again, we shouldn't forget about the monitoring phase. Post-deployment monitoring is needed not only for your pipelines, but also for your infrastructure, your model performance, as well as the new data that are coming. Monitoring also involves creating a data feedback flow, kicking off this pipeline all over again when needed. Let's dive a bit deeper on how an ML infused system is different to a traditional one. In the ML infused system, you bring in data and models, which will explode the number of artifacts that you have to manage. Now, you have data testing, model testing, data and model monitoring, the training pipeline, as well as the standard system monitoring, the end-to-end system monitoring. So things start to get a little complex. You end up with your ML code to be a piece of a much bigger picture with many more assets to manage in a scaled-out ML world. You start having all these challenges, and you now need additional tools and processes. So, what does the MLOps lifecycle look like? Most organizations begin with data scientists and application developers working in totally different environments and ways. App developers are usually more familiar with software development tools and best practices, while data scientists are more focused on the model development and its accuracy as well as performance. So we usually have the data scientist who has got the data and started experimenting and developing the model. Once the data scientist is happy, he or she kind of throws the model over the wall to the app dev who kicks off the build and its deployment process. We now want to start putting some repeatability of the model creation process, which is basically the ability to reproduce the model training process and transitioning to a frozen pipeline, which you can repeat over and over again. As mentioned earlier, with pretty much any ML project, it's not just code that needs to be versioned, but also data and training environment. Data scientists using Azure Machine Learning can capture and track all the artifacts, datasets, environment variables, code, logs, metrics, outputs through the run history service. This allows something very fundamental, model reproducibility. At the same time, developers are working on their code to consume the model. Once you have trained a model that's ready to deploy, you need to test and validate it to make sure that it works as expected in the production environment and when integrated with your app. it's not just about testing its accuracy right after the training is done. It's also about testing it in production, as I said, with the actual use scenario. Once your model is validated, you need to deploy it and get it running. So as I again mentioned before, your training environment might be different to your deployment environment, and that's fine. Azure Machine Learning makes this simple by taking care of model packaging and deployment to a variety of endpoints via containers. You can run models on the cloud, on premises, or in edge devices, wherever your deployment target is. But it won't change this fundamental MLOps pipeline. Last phase is automating the process and to get to this happy or green MLOps state. Management and monitoring of your deployments is also crucial because great models don't always stay great. If, for example, the input data starts deviating from the data that was used to train the model, as I mentioned in the UK weather versus Caribbean island weather forecast example. Azure Machine Learning helps you to manage, monitor, and analyze your models so you know when to retrain. There is a concept of data drift as well. You can create monitors to monitor your data, not just the machine learning model. When models are retrained, you need to build, test, and release your app and the developed model again. And Azure Machine Learning takes care of this by integrating with Azure DevOps so that the retraining automatically triggers your DevOps pipeline for continuous deployment. And it's not just about using a bunch of technologies together. It's more than that. It's bringing this workflow of 3 different personas: data engineer, data scientist, and app developer to collaborate together and scale out. In the ML lifecycle, there is rarely one pipeline to manage the end-to-end process. I highly recommend this shown workflow, which uses 3 different technologies together: Azure Data Factory, Azure Machine Learning, and Azure DevOps, each having different pipelines optimized for the different personas that are involved in this flow. The reason for that is that we have different kind of activities involved. Your data engineer brings data from various sources into a single place and curates the data. Then the data scientist comes in, accessing the data from a centralized data catalog to further perform the data preparation step and then move into featureization to train different models, evaluate the model against their validation dataset, and do hyperparameter tuning. And once the data scientist is satisfied, they register the model. Here, once we get new data, we kick off the build pipeline. Then the ML software engineer takes the model, the persona who kicks off the release pipeline, packages the model along with all the dependencies needed to create that model in a runtime environment, whether it's a batch scenario or a real-time scenario, and then profiles and checks whether you are getting the required throughput for your predictions. This will then need to be approved manually by a human and then gets deployed to your target as a web service for real time. It can be deployed on, for instance, AKS, Azure Kubernetes Service, or on AML, Azure Machine Learning Compute, usually on Elastic clusters for a batch scoring scenario. However, we still need to continuously validate the model with new data to check its performance. And then this whole pipeline gets repeated as new data come in to retrain the model to make sure it meets your standards. As you can see, we have various roles and pipelines involved for the whole process. Just like we have different DevOps adoption maturity levels, we can also talk about an MLOps specific maturity model. MLOps is a journey after all and can be happening at different maturity levels ranging from no MLOps to full MLOps. Let's take a look at the no MLOps situation. It's difficult here to manage a full machine learning model lifecycle because teams are disparate and releases are painful. Most systems exist as black holes. There is little or no information feedback coming from the models during and post deployment. Everything is manual, builds, deployments, testing, testing of model and the application, and there isn't a centralized tracking of model performance. And you also have to train your machine learning model manually in a totally ad hoc way. So now let's go one step up. This is where we have DevOps, but no MLOps. Releases become less painful here compared to a no MLOps scenario, but you rely on data teams to create models every time. That's also ad hoc. And you still have limited or no feedback on how well a model performs in production. And it's difficult to trace and reproduce results. On the plus side, you have automated builds and automated tests for the application code. In automated training environment is fully managed and traceable. It's easy to reproduce a model. Releases are manual but low friction, and you have full automated model training with centralized tracking of model training performance, as well as you can now do model management. And in automated model deployment, releases are now low friction and automatic. You have full traceability from deployment back to original data. You have an entire environment that is fully managed from training to testing to production. You may even have an integrated A/B testing of model performance for deployment. And you have all the automated testing for your code. And you are almost there basically in the full MLOps automation operation. And in the last and final step, you have this full system automated end-to-end, and that's easily monitored. Production systems are providing information on how to improve, and in some cases automatically improve with new models. So you have an evaluation system that checks a new model and says that, okay, this model is better than the one in production, and then it deploys it seamlessly, approaching a zero downtime system. Automated model training and testing exist in this final step. Release automation also, we have it, and that comes with a verbose centralized metrics collected from deployed models. Of course, different organizations may have different paths to eventually enable full MLOps operations, where both model training, testing, and releases are fully automated, creating a zero downtime system. A zero downtime system with robust machine learning inference created in a time efficient and collaborative way, with the extra benefit of having a reproducibility capability. And this is basically where we want to be. With that, I'd like to thank you all for your time, for listening, and I hope it was a useful session. Let me know if you have any questions on MLOps for the Q&A session. Cheers!